Okay, so next we're going to talk about Newton's first law of motion. So this is 3.2 in your textbook. It starts on page 123. All right, or 123. All right, so the first bit talks about Galileo, which is fabulous. You can read about that and his study about balls rolling up and down ramps, because it was thought that for an object to move, there has to be a force causing it to move, when in fact, that isn't necessarily true. So what we need to do is we need to understand inertia, which is what Galileo pretty much did. All right, so what is inertia? Well, I know if you've watched Bill Nye, we say inertia is a property of matter, but essentially that's not enough information. So inertia, it is a property of matter. But there's a little more to it, okay? It's the property of matter that causes an object to resist. Okay, resist means to not do, okay? Resist a change in, I'm going to use the word velocity. Your textbook uses motion, but I'm going to use the word velocity, okay? So things don't want to change what they're doing. You're sitting on the couch, you want to continue to do that. You want to resist a change in your motion or in your velocity. So what does this depend on? It depends on mass. All right, so a bigger box has more inertia, a smaller box has less inertia. It would be easier to push the smaller box, okay, if they were on a surface, on the floor, on a table. This has a lower mass, it has less inertia. It would be easier to change its state of motion, okay? All right, a bigger mass has more inertia. It's more difficult to change its state of motion or velocity. All right, pause. All right, so here is Newton's first law. All right, let's just read it. If the net external force on an object is 0, the object will remain moving at constant velocity. Now, your textbook writes this a little bit differently, but I want you to understand what constant velocity could also include no velocity, because stopped or rest is a constant velocity. So let's draw attention to a couple things that we need to understand so that we can understand Newton's first law. So first of all, we need to understand the word, what is net? What is external force? So net external force, all right, on an object is 0. The object will remain moving at constant velocity. So hopefully we're okay with constant velocity. Constant velocity means that it's moving at the same speed in the same direction. So constant velocity, there's no change in speed or direction. So we'll do that one first here. So no change in speed or direction, because those two things together, okay, combine to make velocity. Now, I'll do the net external force because I want to just talk about net force and make sure we understand the word external force separately, and I'll do that on another board. So you might want to pause right here, copy this down, and I will do net external force on the next board. All right, so the two things I said I would discuss, net force and external force. I'm going to do these separately. All right, so what is net force? It really is, when we talk about net, and if you're taking any kind of accounting class or something like that, or what's the net worth, it really just means the sum of all the forces on an object. Okay, so essentially when you sum, you add them up. Okay, you add up all the forces. It's not a question mark. Add them up. Okay, you add up all the forces, and that's how you get net force. Now, external force means exactly what it means. So if I'm talking about a car, how do I make that car move? Well, an internal force, if I'm pushing on the steering wheel, all right, and I'm trying to push on the steering wheel, that's not going to make the car go. I need to place an external force, so on the outside of the object. So this is external, okay? This would be, if someone was pushing on the steering wheel, this would be an internal force. All right, and we can actually even have a equation for net force. Maybe we'll do that on the next slide because I've run out of space. Or actually, I'll just erase this. So external force on the outside of the object, internal, inside. The car's not going to move. So we always need to be talking about external force when we are talking about Newton's first law. Okay, so what is net force? F net. You just add them all up, however many forces there are. This could go on forever. Usually we don't have more than a couple, but F net is the sum of all the forces on an object. Okay, there we go. All right, so here we are with a couple examples from tutorial 1. We'll do the same thing as I did in the last one. Essentially, the textbook says, use Newton's first law to explain each situation below. Why does a computer sitting on a desk remain at rest? So we'll do that one first. So here's a computer sitting on a desk. Well, the first thing we need to do is what are all the forces acting on the object? So you can do your computer, it's a dot. We're doing FBDs because we are going to use FBDs to describe why these things are all at rest, since inertia has to do with being at rest or moving at constant velocity. In terms of the computer, we're doing it at rest. So here's the computer. It's sitting on a desk. So there's the force of gravity, and the sitting on the desk is a normal force. And those happen to be equal forces and acting oppositely on the computer. All right. So here, F net is 0. All right, so F net is 0. That's why it's remaining at rest. As long as F net is 0. All right, now that doesn't mean that there's no forces acting on it. It means that these two forces together add up to be 0. All right, a puck. So a puck moving across smooth ice at a constant velocity. So it's moving. So here's my puck. Okay, it's moving at a constant velocity. It's moving that way. What are the forces acting on the puck? Now, the puck obviously was pushed at some point, but is the puck being touched right now? In the question, it says it's moving across the ice at a constant speed. It's sliding across it. So there's no applied force. But what is there? There is a normal force because it is touching the surface of the ice and it's on Earth. So there's the force of gravity pulling it down. Now, do these two free body diagrams look different? If we even disregard my little squiggly arrow here, they look exactly the same. Why? Because they are both moving at a constant velocity. This one is stopped. This one is moving at a constant velocity. They are both essentially the same. They're not changing their motion. All right, so stopped, moving at constant velocity. Like I said, this is my own thing. This is not a force. It's just saying it's moving to the left. Now, number C, why does a wagon pulled across a rough surface by a child move at a constant velocity? Well, here's the wagon. If you want for this one, I'll show you by using a box. So sometimes I do it with a box. Here's a wagon. Well, it's on Earth. and it's on a surface. If it's touching a surface, these two forces will always be here. And if it's not moving up or down, then they are balanced. So there's my two forces, but this is being pulled by a boy. In the question, so we could put F boy. And are these forces balanced? No. So this wagon is not moving at constant velocity, so there must be another force acting to the left, and that would be the force of friction. And that will balance out the force of the boy is pulling on the wagon, and here F net is 0. Because this adds up with that, and they're in opposite directions. The boy and the friction are in opposite directions. So we could make up some numbers here if we really wanted. So let's just make up some numbers. Let's say this is 12 newtons down. Then this must be 12 newtons. Whoops. 12 newtons up. And if we added those two numbers, we know that up and down are different directions. So one of those would be negative, whichever one you decide. And if the force of the boy was 22 newtons to the right, okay, then the force of friction better be 22 newtons to the left. And then in all of these cases, F net is 0. If we think back to Newton's first law, if the forces are balanced, then the object will remain at a constant velocity or at rest. Same difference. Now, there are a lot of implications and technology that help us control our inertia. So we're going to talk about that one next. So I'll pause here. You guys can pause and get those down. All right, so let's talk about Newton's first law and driving. And there's a bunch of reasons that understand Newton's first law is important. I mean, it's why we created seat belts, headrests, and why it's important to know what items can you actually put on a dashboard. So if we think about seat belts, as you're driving in your car, if you stop really fast, so here's my car, like in the other one, and you think about yourself sitting here in your car driving, la, 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 and you stop fast. So your car stops. What do? Well, some people say, oh, well, you move forward, but you're actually not, sorry. Are you moving forward? Yes, but we have seat belts to control our inertia. So when the car stops, we are attached to the car so that the force from the brakes that's applied to the car also stops you. We don't want to end up going through the windshield or hitting our heads on the dashboard. All right? So seat belts are a perfect example of how to control our inertia. So what happens is the car stops, but we continue at our state of motion unless something like our seatbelt acts on us and takes away that motion and changes our forward velocity. All right? Headrests are the same idea. It's important to actually have your headrest at the right place. So if I have my head here, and in a long time ago, there were no headrests. So you're driving along, la, 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 in your textbook, you stop and your head continues forward, but then it also comes back because your seatbelt is pulling you back. So if this headrest wasn't here, all right, the seatbelt is trying to change your state of motion. Your head will go back, bends your neck, and gives you whiplash. So headrests get rid of that and actually stop your head from moving backwards. It actually controls your inertia. So headrests control your inertia. Seatbelts control your inertia. Placing items on the dashboard, okay? Or we could even think of a cup in your cup holder. If you don't have a lid on, that liquid sloshes around. There's no force being applied to it. it is applied on the sides, but liquid is free to move. So just like items on your dashboard, I want you to think about what happens to those items on your dashboard when you stop, okay? They are going to continue forward in their state of motion. But what happens when you accelerate fast, like from, you didn't notice that the green light changed. So let's say here's my dashboard and you have, I don't know, your homework sitting here and you accelerate quickly. Well, if there's not any friction here, it would appear that your homework moves backwards. But is your homework moving actually backwards? No, your homework's not moving backwards. What's happened is the car has moved out from underneath your homework and falls down. But since you're in the car, you've moved forward. So this is kind of what relative motion is about. So yes, the car moves forward and moves out from underneath whatever's on the dashboard and it falls down. But sometimes we interpret that as it moving backwards. Not true. Okay? All right, so now let's do a demo. You can actually do this at home. You just need some type of coin and a piece of maybe cardboard. I just ripped this off of a package of pencils I have sitting by my desk. So what you want to do is you want to balance the coin on your finger on top of this piece of cardboard. You might be able to try and use a piece of paper. I think it might be too flimsy. So what you want to do is you want to flick, and you need to flick at just the right angle so you apply the force only to the paper. So I've practiced this a couple times, not on video, and we'll see if I can do it on the first time or if I have to do it a couple times. So here we go. What's going to happen? I wonder. Well, I did it. Okay. Now this is similar to a magic trick that you see magicians pulling tablecloths out from underneath. So why don't you try this? Have some fun with that. And I'll do a couple of, calculation examples for Newton's first law. But I want you to think about how you're applying the force and why isn't the coin moving. When we're done all of Newton's laws, we'll have an assignment related to this. So practice this and have some fun. All right, so let's do some calculation examples. So find the unknown force if the following objects are at rest or moving at constant velocity. So this is example 1, and then I'll do example 2. So to find the unknown force, all right, I can see that there's a couple forces. I'm told that it's moving, it's either at rest or constant velocity. So that means that I know that F net is equal to 0 newtons. Okay, but F net is also equal to the sum of all the forces. So let's write out what F net is. It's equal to the sum of these 3 forces. F1, F2, and the force of gravity. Now, I know that they're all equal to 0, so they're going to add up to be 0 newtons. I put the line through here because sometimes it looks like the word on. Well, I know what F1 and F2 are. I'm told that it is 12 newtons up and 8 newtons up. But I don't know the force of gravity. Now, you probably can do this question a lot faster than me, but I'm doing it the long way because I'm teaching you. So 0 newtons, and since these are in the same direction, I can add these up to be 20 newtons up, plus the force of gravity. All right? Now, I think I'm running out of space, but what I'm going to do is I'm going to subtract these on both sides. So what I'm going to do is I'll pause right here if you want to pause and copy this, and I'm going to erase a bit and finish the question. All right, so here we are. I've just erased that and moved my last line up here. So if I was in a math class, what do? Well, these are on the same side. I want to get rid of the 20 newtons, so I'm going to subtract 20 newtons on both sides. So negative 20 newtons up equals Fg, and I have my answer. But let's make sense of that. What's negative up? All right, so I want to solve for FG. Well, negative 20 newtons up is just the same thing as 20 newtons down. So the force of gravity is equal to 20 newtons down. And that makes sense because it's 20 newtons up. What's going to balance that is 20 newtons down. So remember, if we have a negative in front of a direction, it's just equal to the opposite direction. So negative up equals down, or negative down equals up. We did that and knew that from the last unit. So pause here. All right, so here we are with our second example. All right, so I'm still finding the unknown force, and my object is still either at rest or constant velocity. It doesn't matter which one, okay? That means I know that F net is equal to 0 newtons, if it's one of those situations. So this one is a little bit more complicated because we have both vertical and horizontal forces. But what we want to do here is we can actually take these individually. So I will do the vertical first. All right, so we're doing vertical first. So F net, and I'm going to look at how many forces there are. There are 2. There is the normal force. And you know what? I'm going to write this a little bit differently. Why don't we just write Fn plus Fg equals F net. And maybe this will make sense why I did this. Well, it doesn't matter where I put the F net. I know in the equation I said it's F net equals, but I know I'm solving for Fn right here, or normal force. Don't get confused with net and normal. They both start with N, but this one is a capital N. So this is what I'm looking for, and I just thought, oh, why not arrange it so that it's easier? So here we are. This is 22 newtons down. I didn't put the direction, but I can get that from the FBD, or the free body diagrams. That's 22 newtons down. And F net, I know, is 0. Okay? So if I do my math and subtract 22 newtons down on both sides, I get Fn equals negative 22 newtons down, and negative down is actually up. So the normal force is 22 newtons. Okay, so if you need to copy it, pause here. I'm going to erase and do the horizontal components. Okay, so now I'm going to do horizontal. Okay, so horizontal is like left and right. If you've forgotten, vertical is up and down. So in the horizontal, I have 3 forces. My situation hasn't changed. It's still Fn net. F net is equal to 0 newtons because it's moving at a constant velocity, or it's at rest. Either way. So there are 3 forces involved, F1 plus F2 plus F3, and that equals F net. So you'll notice here that the first line I have very general. I have arrows, vectors on all of them, and that's why I put direction in. If you want, I'll do this one a little bit differently because some of you did drop your directions. I know it makes it easier for some of you. So I will do this one that way just so you can see me do it. So F1 is the one I'm looking for. So I don't know anything about it, so I'm going to write it down, even with the arrow on top. Then I'm going to write down my forces with the direction. So F2 is to the right, so it's 28 newtons. And I'm going to use an R for right, plus F3, and that's 15 newtons to the left. 15 newtons to the left, and that equals 0. I can fit that in. You guys can see that. All right, now, one of the ways we did this before was to choose a direction that is positive. So why don't I just say this direction to the right is positive. Now, when you do it this way, all right, you interpret the directions as a sign. So if it's to the right, it's positive. If it's to the left, it's negative. So it does make your life a little bit easier. So this is to the right, so it's going to remain 28 newtons positive. And this one is to the left, so I'm going to interpret that as a negative. So this is negative 15 newtons, and I'm still equal to 0 newtons. So then we just simplify and do the math here. All right, and so we have 28 minus 15 is going to be 13 newtons. We still have that being equal to 0, and then I have to subtract 13 newtons from both sides. So this ends up being negative 13 newtons. Now, what's this negative indicate? This negative indicates direction, just like it did before, but I don't have this one here. So I still need a final answer because I need to have a direction here. So what you need to do is interpret F1 as 13 newtons to the left, okay? Because essentially when we changed all the signs, this really was to the right, okay? So my final answer is 13 newtons left. All right, pause if you need to copy that.